Now, it's very nice to see you all. Very happy to see you. And we are going to have different topics. First of all, we see new faces here that we haven't, well, I suppose, with the lack of periodicity in these meetings, by the time we come to the next meeting, we forgot who is who and who comes from where. But it would be nice to say a few things about us, especially the new ones that have come. Please, you can just say something about your background. Why are you here? What you're expecting? And nothing very sophisticated, but just to introduce yourselves. And then we want to have a little community really to know each other. Because once we start the course in September, you will see it's very communal. It forms like a little family with the chat in the WhatsApp. Becomes quite a nice friendship that we get usually. The last 3 or 4 years, it has been like that. So who would like to say something? I will say something about myself. I am from Mexico, obviously. It's a very strong accent. I cannot get rid of it despite many years of being here. We never lose that accent, especially when you learn your language at a at an older age. The children can adopt any accent without any problem. Come from Mexico. My first degree is in mechanical engineering. I have been an amateur astronomer all my life since I remember, taking pictures, looking at the sky with my own telescopes, which I built myself in the beginning. Now telescopes are becoming more available. And the one you saw, I used this afternoon to take pictures of the sunspot. It's a telescope I just bought. They are not very expensive, really, and they are super quality. So I enjoy very much that. I came here to the UK to do a PhD in astronomy ages ago in UCL, and I still work at UCL as a lecturer and as a public outreach organizer of festivals and major events, really. And at the moment, I am embarking in I would say a movement. It's not a project, it's a movement on education of science. And the first part that we are going to cover here is part of that project about the nature of the universe, about the nature of matter. So we are going to do that. So, and my main lecturing is in undergraduate students. I was doing that just now until a few minutes ago. And of course, the lecturer as your lecturer in the certificate of astronomy. So that's about myself.
Oh, okay. Just wanted to say that I used to travel in Mexico, and they all thought I had an accent when I was in Mexico. So, you know, tit for tat there. So I'm a retired engineer, mechanical, just interested in astronomy. I attended a 1-week course at UCL with Francisco as the chief man. Really enjoyed it and looking forward to the astronomy course next year.
Thank you, Peter.
My name is Adrian. Sorry about my camera. It's not working in my laptop. I'm from Spain. I've been here already for about 9 years. Yeah, I mean, I moved to London 2 years ago, and I saw straight away the diploma that UCL is offering. However, during these 2 years, it has been impossible to run it. So I'm looking forward to next year to finally start.
Thank you, Adrian.
Hi, I am Sylvia. I did also the 1-week course at UCL, the Mill Hill Observatory with Francisco 4 years ago. And yes, and since then I'm trying to study astronomy.
Thank you, Sylvia.
Kate Alien live from Wimbledon. So apologies about that, as my husband named us, and it just seems too complicated to try and change it all the time. So apologies for that. And I just want to say thank you.
No, wait, no.
Well, and thank you to Adrian for sorting out the WhatsApp group. That's really kind of him, and we've had a lot of communication on that, and it's been great. So thank him.
Hey, my name is Saurav. Not sure if you all can hear me. If you can't speak up. So this is my first session joining you guys. Very pleased to be here. It was completely by chance that I found out about the certificate program to begin with. And then when I communicated with Francisco about these weekly programs, and I'm delighted to be here. I used to live in Hampstead, close to the Hampstead Observatory, and I volunteered there for some time, for a few years, when it would be open to the public on Friday evenings and Sunday afternoons. I figured that, it was very interesting and got to see a lot of beautiful sights, but I didn't retain much. I didn't learn much, or I couldn't keep much of whatever I learned in my head. So I figured the best way to go about crystallizing all that knowledge that I picked up from just hanging around enthusiasts is to join a course such as this one. So I'm glad to be here. Somebody mentioned, Adrian, perhaps you started a WhatsApp group. Please do add me to it. I would be delighted to participate and look forward to meeting up with all of you when sessions start in September next year.
Thank you very much, Saurav. Right, I think that's fine. Look, if you write anything in the chat, I won't be able to deal with the chat. I am on my own, so I won't be able to read it. Occasionally, I may come. If you wrote something that needs attention, please let me know, and then I will read it. But I prefer if you could open your microphones. Sorry, Alexandroni, you have your microphone open. Would you like to say something? No. And Chris?
Hello there. Sorry, whoops. Sorry, I had problems joining. I had to download some software. Can you hear me now?
Yeah, it's fine.
Good. Okay. Shall I introduce myself for those who I've not spoken to before? I sort of did some of the course before, but I had to, for personal reasons, I had to stop the course, and I'm very fortunate and hope to join the course again in September. I've obviously had a privy to some of the course, having done some of the course before at UCL, and it's I can just say, it's completely changed me. The course is really interesting, and I think the whole topic, not just the course, but the universe and everything is just fascinating. And I think we're very lucky with what's going on at the moment with all the progress with the space programs. And I was even talking to somebody the other day who are sort of just changing jobs, and their brother-in-law is involved in the James Webb telescope, and indeed used to work at the observatory down in Chile. He's Mexican. It's a fascinating world. I thoroughly enjoy it. I'm looking forward to being back on the course in September.
I can introduce myself briefly. I lost my connection a little while ago, so sorry about that.
Oh, lovely, Chris. Nice to see you back. That's really nice. I think so. Yes, Sam, I got your best.
I'm really sorry, guys. My connection's really breaking up. I'm not. Maybe I'll introduce myself another time, because I can't quite hear where I am and where you guys are, so it's a bit confusing for me. But I'll try to listen in if that's okay. So,
well,
sorry about that.
If you prefer, just kill your camera and just keep the audio on.
Yeah, Francisco, I think the same thing's happening as last time.
Okay. Yeah, maybe that's better with the
right.
video off. Yeah, just I'm really fascinated by astronomy, and I love reading about cosmology and the history of astronomy. from Aristotle up to the present day. I don't have much experience in practical astronomy. I did go to Chile to visit the very large telescope, and I stayed for a while at a wonderful observatory run by a French astronomer called Alain Murray. And yeah, it was just magical to be out there under a really clear sky. It's something that we unfortunately don't get to enjoy living in a big city. So when I learned about this diploma, it just seemed a great opportunity to learn more.
Fantastic, Sam. Thank you very much. And I would say that going to Chile, to the Atacama Desert, it's a major experience. And I hope in the next future we can organize a trip there. You know, after we finish with the course, with the 2-year course of the certificate, there is a kind of alumni group that has between 300 and 400 alumni from this certificate that has been running for nearly 20 years. So that group organizes trips to eclipses. This eclipse coming, the next new moon will be a total solar eclipse in South America. Probably we cannot go, but some people organize the tours. Certainly going to the Atacama Desert is a major thing to do, especially the telescopes there. That place that you mentioned, Alain Murray, we are good friends. He used to work for the ESO observatory, which is not far from there, and he runs this bed and breakfast with a massive telescope. In the future, we can organize something to go there, because as you said, Sam, it's a really good sky in the middle of nowhere, at very high altitude, in the middle of the desert, and it is really impressive. Right.
Yeah,
so anybody
it's really
else?
magical.
Sorry.
No, I was just going to say it's really magical, and he gives you amazing hot chocolate if you go there.
I remember I commented that to you. Yeah, that was the most important thing. Yeah. Okay. Anybody else would like to say something? Right. So we are going to start. I'm going to share my screen. I'm going to tell you a little story. Little, not that little. So let me start with this. Can you see that?
Yeah.
It's a lovely picture, isn't it? I'm going to tell you that we see a variety of materials here. We see objects which are in the distance, and we see objects which are nearby. The ones that are nearby are alive, we know that. They are plants, they are trees. And far in the distance, we see things made out of rock. We see snow, and above that, we see a blue, what we call the atmosphere. So I'm going to ask you to forget, or try to forget, or try not to consider what you know about all these things. We're going to see that in a different way. We can ask, where do we live? What is this planet that we call Earth? Where does it come from? What's it made of? How long has it been here? We are going to explore the night sky. The night sky that we see in a clear night out of light pollution is a challenge for humanity for thousands of years. And no doubt a view like this has been the driving force behind the progress of the human intellect. Without this view, humanity probably wouldn't have developed the way it has. It's an inspiration for many reasons. So where does this come from? Where are we? How can we make sense of this? There are plenty of stories, plenty of myths, some of them still alive today. of all the cultures around the world from all times, and still we don't have a proper answer to this enormous question about the origin and the destiny of where we are. Now, in order to explore this landscape, we are going to make a few analogies. Here we have a city which has a lot of structures which are very different from each other. There is a lot of diversity, a lot of complexity. It's a very complex system that we see here. And it is, in a way, misleading. It's deceptive. We have cities all around the world made out of a variety of buildings. The buildings are very different from each other. And we can ask how all this came to be. Well, we have to go into the smaller components of these structures. And if we go closer and closer, a pattern starts to emerge. We can see a pattern that, despite that the buildings are so different from each other, the pattern is repetitive, is always the same. This pattern that we see here is a pile of bricks that will produce walls. The walls will produce rooms. The rooms will produce houses or buildings. The buildings will produce cities. So in a way, the complexity of a big city can be reduced to a pile of bricks. The buildings are very different. The complexity is very enormous. The diversity of structures is enormous. But it comes to a simple structures like this one. If we can go even further, because the bricks are made out of grains of clay and sand, so everything becomes to a simple thing. So the very complex things become very simple when we go to components. Now we realize that there is a sequence here. We cannot have a city without houses. We cannot have houses without walls. We cannot have walls without bricks. We cannot have bricks without grains of sand and clay. So there is a sequence. So we have to have the clay first, we have to have the bricks first, and then we go in that sequence. So what we see here is a process of assembly. We are not creating a city. We are not creating houses. We are assembling them. We are putting them together. We are taking building blocks, components, to put them together to give the impression of something that is just an assembly of individual parts. And that is very important because this is the fundamental concept of the structure of the entire universe that we can see. We have other analogies. This analogy comes from art. Children, even today, and no doubt when we were children, we were doing this, just making, like the Aboriginals, and like in Australia, like the North American tribes in New Mexico, mainly painting with grains of sand. So we have done this technique, which is called the pointillism, made with little points, little dots, to create the illusion of something which is big and more complex and with more structure. So we have many analogies. There is another one here. Our mobile phones have a variety of colors, a variety of structures. We can really reproduce any color, any shape, any images, all the images that we see, including the one I'm looking at exactly right now. And you yourselves are looking at images creating in the screens of your computers. And the screens of your computers come to a very simple structure. If we we go closer and closer. We take this image here. You can see my cursor there. This image here that says photos. We go closer to that. We zoom in on that. And we start seeing a little bit of like bricks structure emerging there. And we go closer and closer. And we can see that the colors are made out of little squares. And if we even closer with a proper microscope, we can see this. Those colors that are magentas and oranges and yellows and all that, they all disappear. All we see here is blue, green, and red. That's all we see. So all these enormous millions of colors that we see in our screens are made out of the mixture of the primary colors, which are red, green, and blue. And these colors mix together in different intensities to give the impression of any colors we can imagine. So this is an amazing example of the simplicity of this image coming to the complexity of the images that we're to see, the ones we just saw before of the city and the bricks and the grains of sand and all that. So here we have this example. If we have the three colors, red, green, and blue, together with the same intensity, we get white. Amazing, isn't it? The color white. Take away the green and the blue, and we get red. Take away the green, and we get cyan, magenta, which is a mixture of blue and red. Magenta. And then we can go on and on about the different colors that we see here. See, here is red, green, and blue together. That's white. Here, that's white. So the very simple structure of three colors can combine, can assemble in a multitude of colors and patterns that we can assemble in modern images, but it comes all to that. I leave you to reflect a little bit on this. Just reflect, just think. Don't think about asking questions, just to reflect on what we have seen now. So now we embark in another venture here. This is the totality of the colors we can get from different mixtures. We have all of them as white in the middle. Yeah, and then we have the different, the primary colors are in these corners, the red, the green, and the blue. And then the secondary colors come as a mixture of red and blue. We got magenta, and then the red and the green go to yellow, and the green, repeating the names of the cartridges that you have in your printers. Cyan, magenta, yellow, and black. So these are made of things, so more like they look to each other, and the smaller things come always first. That is very important in the history of the universe. How small? Take the droplets of water. How small, you can see here, it's here. How small that can be. You may remember this picture or similar that I was circulating a few days ago in the WhatsApp. So these droplets of well, we say water, I mean, it's dew, is nothing. How small are they? Isn't that beautiful, how these things happen, of a mixture of the moisture in the atmosphere with the hard work of spiders, plus the action of gravity, plus the action of surface tension in the water. Isn't that amazing? It looks like jewels, it looks like a necklace of will pale against the beauty of all these things. How small can they be? At the scale, this is 1 millimeter.
While we're waiting for Francesco to come back, does anybody have an interest in meeting up to discuss chapters of the Universe book every week or so?
Yes. Are you in London?
Yeah, I was thinking of doing it by Zoom.
Oh, okay.
That sounds like a good idea.
Yes, if you have that, I mean, you can always use the chat in the WhatsApp, and then we can organize something. Okay, let's see. How many particles of the smallest amount of water that we can have will fit in a little droplet like that, which is 100th of a millimeter, say, in size. And the analogy is as follows. We are going to make an analogy with the number of millimeters that we have between two places in the universe. You can imagine that you can see me. Can you see me doing this?
Yes.
Yeah.
The distance between my two fingers here is about 100 millimeters. Yeah, 10 centimeters, 100 millimeters. So 1 meter will be 1,000 millimeters. So 1,000. So let's keep going. Just to make the long story short, it's a very long story, and it's not short. The number of millimeters between here and the moon, which I can see there, still there, it's getting clearer actually. The amount of millimeters between here and the moon is enormous amount of millimeters, okay, millions. That's not enough. The number of particles in that little droplet is more than that. So the moon is about 400,000 kilometers away from us. Each kilometer has 1,000,000 millimeters. So we have 400,000 million millimeters from here to the moon. 400,000 million. That's a lot. If we imagine that the population of the Earth is 7,500 million, this is 400,000 million. That's nothing. We need to go away from the solar system. We need to go to the nearest star, Alpha Centaurus, to find out that the number of millimeters in 4 light years, the moon is only 1 second of light away. 4 light years will have an enormous amount of millimeters, and that number of millimeters is equivalent to the number of water particles in that little droplet of water.
Wow.
Okay,
Wow.
just let that sink in, because listen, I calculated this a few days ago because I wanted to tell you this, and I had to do the calculation several times over because I couldn't believe it. So that tells you how small the universe can be. And that number was, I don't know, it was trillions of millimeters. But it's a matter of feeling it. You see, you cannot imagine that number. It's a matter of feeling the number of millimeters between here and the nearest star, and the water particles in this drop is more than that. And there are more analogies actually. So those water particles that we call particles, they are molecules, and they are very simple molecules. They are made out of 3 atoms. And the atoms, we are going to see what an atom is in a minute, but the atoms have 2 sorts of atoms. The white ones are hydrogen, the red ones are oxygen. We will see all that in a minute. And they put themselves together to form water particles, droplets of water, of rain, and then oceans, rivers, and lakes, and oceans elsewhere in the solar system, and the rest of it, all made out of this molecule that has 2 hydrogens, white, and 1 oxygen in this angle. That angle is defined by electric forces between these atoms, and that angle is about 120 degrees, more or less. And that angle defines the shape of snowflakes, for example, that we will see. Hopefully, we will see them, because if we don't see them, that means the global warming is quite strong. I hope we will see some snow this winter. So the question is, now we have these particles that get together. Obviously, they have to assemble together to form water, but they are not together all the time. They have to come from somewhere. So originally, we have 2 hydrogens and 1 oxygen separate, and they have to come together somewhere, sometime, and then to form the water molecule by the millions and millions and millions. And we know that water like this, molecules, they are very abundant in the universe.
We know that the comets are made out of mainly, have a lot of water, and there is a lot of water in the universe. That's where the water is coming from, H2O. So where is water made? Where is water assembled? Because it's not made, it is assembled. You got to take 2 hydrogen and 2 oxygens and glue them together to get a water molecule, let alone trillions and trillions of them. Another example is sugar cubes. We have particles of sugar. The sugar cubes are like bricks. And we can imagine that these grains of sugar are going to make bricks, and the bricks can make together a lot of structures. But the grains of sugar themselves are made out of atoms as well, hydrogen and oxygen that we know already, white and red, and the gray ones are carbon, and they get together in this particular shape. There are many types of sugars. This is a very simple one to make sugar. Where is this happening? You need to have hydrogen, carbon, and oxygen. You have to put them together somehow, somewhere, sometime. Where do you get the sugar from? Isn't that amazing, all these questions? 2 carbons, 2 oxygens, and 4 hydrogens in this case. So here are the fundamental chemical elements that we will see, the fundamental chemical elements for life. Carbon, because this is the color of graphite, the color of the pencil you write with, the graphite. Red, because it's the oxygen that is carried by our blood. The blood is red, just to remind you, carbon, oxygen. The blue one is nitrogen, which is the most abundant molecule or element in the atmosphere, which is blue. And then finally, the color of clouds, which are made out of water, hydrogen. So hydrogen, nitrogen, carbon, and oxygen. This is a general convention to color code in chemistry for these fundamental atoms. So if we have chocolate, for example, which is made out of these particular atoms we mentioned, the molecule is a little bit more complicated. It has this structure, but still the same colors, you see, carbon, nitrogen, oxygen, hydrogen. So that is what makes you happy, or me happy. We were talking, I mean, you drink a lot of this when you go to the Atacama Desert, for example. They give you this hot chocolate. So that's a chocolate molecule. So where do we get the atoms from? It's fine to have oxygen and nitrogen. Where are they coming from? What are they made of? Can we look inside an atom? So electrons. Then inside we have little particles, red particles, 1 here, 2 here, and 6 here. 1, 2, 3, 4, 5, 6 red. No blue particles here, 2 blue particles here, and 6 blue particles here. So the yellow ones here outside are the electrons, the red ones are called protons, and the blue ones are called neutrons. And they are all identical from each other. This is extremely important. Remember the analogies we have been carrying from the colors, from the grains of sand. So here we have 3 particles, only 3, that produce all the atoms of all the chemical elements. Only 3 particles. The only difference between atoms is the number of particles. That's all. So that is extremely important. And a lot of us know that, but it's important to assimilate that and to be aware of the importance and the relevance of this simplicity of the universe that comes to that. So that's where we can we get the atoms from. We get a bunch of protons, a bunch of neutrons, put them together, electrons around them, and that's it, atoms. Where do we get the protons and neutrons and electrons from? Where do they come from? And you have to imagine that we cannot have water without having atoms first. We cannot have atoms without having these particles first. So there is a sequence there in time. And that sequence comes from here. What we see here is a picture that is impossible. It's a picture of the origin of the universe. That it was a minute point of pure energy. And that pure energy emerged out of nothing, as far as we can tell, violating all the laws of physics as we know them. And we called it the Big Bang, although it wasn't that big, it was quite small. And that was pure energy. And with the emergence of this point, that energy, which is an infinite amount of energy, practical infinite, I mean, it's an enormous amount of energy at enormous temperature, and starts to expand. This is the only act of creation in the universe. We are going to see that in the course properly later on. But that energy expands very quickly at an enormous speed, and that expansion cools down the original temperature of that point, and then expands, and the expansion keeps going since. And this is thousands of millions of years ago. That expansion is cooling down the universe, and with the expansion and the cooling, the energy is going to transform. We have this kind of cloud of energy. There is no material here, it's no matter, it's just pure energy. We can imagine that. That energy is transformed into particles, and these particles are the fundamental particles, if you like, the fundamental pixels of the images, the fundamental grains of sand of cities, the fundamental grains of sand, the fundamental particles of the entire universe that we can see. It's very important, the universe we can see. So
Francisco,
have a look
can I
at
ask
them.
a question?
Yep.
Can I ask a question, or shall I wait for later for the end?
Well, it depends.
I'm wondering, the energy must be carried by something, right? There's got to be something tangible which carries the energy. So if it's temperature, something's got to be hot. If it is light energy, there's photon.
Okay.
There's got to be something, no?
No, we are not going to that. We are going into that. Yes, I agree with you. It's a sidetrack, enormous sidetrack. This is full of sidetrack possibilities, and it is very difficult to cope with that. Some of these sidetracks are open things that go to abysses. I mean, they go to the cliffs with no answer so far. So we have to be careful. But it is the point is that there was no matter. There was no material in that energy. And just to give you an idea, that cloud that you see here of pure energy is the shortest period of epoch of the universe. It lasted after the emergence of the point of light, of energy, say, it lasted a trillionth, billionth of a second. Okay, you can imagine a thousandth of a second, a millionth of a second, a billionth of a second, a trillionth of a second, let alone trillion, billionth of a second. Very short period of time, after which the transformation occurs, the energy cools down, and it sort of condensates in particles, three of which are the particles that integrate the entire universe we can see. And here are the yellow ones, the electrons, and the red and the blue ones. In this case, they are not protons and neutrons, they are quarks. We call them quarks, or the physics call them quarks for historical reasons. You can investigate yourselves. There are a lot of interesting names of all these particles in the particle zoo of modern physics. The red quarks and the blue quarks. The red quarks are positive charge, the blue quarks are negative charge. They are fundamental. You cannot break them. If you break them, you get energy. The electrons are fundamental. There is nothing inside them. Nothing. They are fundamental. That's a very important thing. And I have to tell you, everything we see in the universe, everything, absolutely everything that we can see in the universe is made out of this. Stars, planets, people, whatever. It's like all the images that you can imagine in screens are made out of red, green, and blue brick. Well, same thing. So is the analogy that we have here. So that's how simple the universe was for a fraction of a second. This was a little bit longer. It will take a billionth of a second for the next stage. Not trillion, it will be billionth of a second. Imagine that we are giving a Lego set with different particles, and we have to put them together and assembling them. We need to put them together. We need different glues. We have strong glue, weak force, gravity, and different kinds of glue. We're going to put these particles together. The quarks get together in 2s and 3s, and 3 particles, 2 red and 1 blue, or 2 blues and 1 red. You cannot have 3 reds and 3 blues. No, it's only, they have to be different. So there are only 2 options there, positive and negative, negative and positive. And what you get here is combined particles made out of quarks that are protons, end up with a positive charge, neutrons with 0 charge, and the electrons remain fundamental to the day. They haven't combined in the same way. They have been confined. So this happens in a billionth of a second, and in a billionth of a second, the universe has produced all the protons, all the neutrons, all the electrons of all the atoms of the entire universe. We had to stop and swallow that. Billionth of a second. 1,000 millionth of a second. Isn't that amazing? So the process continues. We have some of the glues putting protons and neutrons together. And this is happening at the beginning of the universe for a few minutes. We get the fusion of these particles and the production of a cluster of particles, of protons and neutrons that have to be put together at very high temperatures here while the universe is still very hot. And then we end up with particles, with the nuclei of what will become atoms of hydrogen and helium, mainly in the fraction in the proportion of 3 to 1, which is what we have today. The universe is made out of 3/4 hydrogen, 1/4 helium, and the rest is only traces of all the other chemical elements. So this is the early part of the universe, and the process goes for another few million years, the dark ages of the universe, when we have the first stars that come out of that cloud of hydrogen and helium. And this is where the universe starts to get interesting. And when you get the stars, where the clouds get very compact and very pressurized, very hot in the center, and in the center at millions of degrees, we continue with this process for nuclear fusion. What happens is putting protons and neutrons together, assembly, 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 larger and larger numbers. We end up with helium here. If we keep going at higher temperatures, 100 million degrees in the center of the stars, we get more and more particles put together, 8 in this case, 4 and 4, 6 and 6, 8 and 8. This will be a nucleus of an atom of beryllium. This will be a nucleus of an atom of oxygen. And this will be a nucleus of an atom of carbon. And the process keeps going. That's the carbon, keeps going. When the process goes to a point that the star dies and explodes, the explosion of the star will produce temperatures of thousands of millions of degrees, the supernova explosions that happen very frequently in the early stages of the universe. And in these explosions, we have the remains of the stars that travel into space. And that's where we have the possibility of these forces bringing protons and neutrons together by the hundreds. And this is where we get the rest of the chemical elements. In these clouds that were stars, we find now traces of silicon, oxygen, of course, and carbon, but also uranium and gold. And this is where we get the chemical elements of the periodic table. I will stop here just to let you know very quickly how the universe develops this chemistry, because we need this chemistry to assemble the landscape that we saw at the beginning with mountains and plants and flowers and atmosphere. All that is made out of these chemical elements, including our own bodies, of course. So this is a familiar picture of the periodic table, but I have broken it into 3 components. The ones we have here on the top left are hydrogen, helium, and a little bit of lithium. They come from the Big Bang. And then the universe cools down, and we need the stars to continue with that, because the stars bring back the very high temperatures because of the pressure inside the stars. We get the millions of degrees back, where we can put together more or less, I mean, give or take, because there are different processes here, but in rough terms, we get chemical elements all the way down to 26. The numbers we see here is the number of protons in the nucleus. Remember, 1 for hydrogen, 2 for helium, They say 4 beryllium, 6 for carbon, 8 for oxygen. And then we go down all the way to 26 protons, 20 for calcium, very important for us, and then 26 for iron. At that point, the stars die. They cannot produce anymore. They cannot assemble more protons and neutrons together. The stars explode. And during the explosions and after the death of the stars, we have the conditions of thousands of millions of degrees where all the rest of the chemical elements, the metals, essentially, there is the silver and gold and mercury, cobalt, nickel, zinc, all these uranium, palladium, all these chemical elements that are so lead, that are so familiar to us, some of them very rare, like gold and silver, and uranium very expensive, very difficult to obtain because they are mixed with many other things. But they come from the death of the stars. So that's where we get the chemical. Now the chemical elements for life are here. They are hydrogen, as we said before, carbon, nitrogen, oxygen, and then phosphorus as well, because DNA contains a lot of phosphorus, the molecule of life, all these chemical elements. So that's the story that I wanted to tell you, is the assembly process of very simple things like quarks and electrons that can put together in different stages, in different conditions, in different places, especially inside the stars, to assemble themselves together and produce the chemical elements out of which the process of assembly will continue again and again and again to assemble into new generations of stars and planets and people. So that is the nature of matter. And I'm going to stop sharing. I will put my camera on now. And we are going to stop here and have a little bit of reflection. If you have anything to say, I think you can open your. I think the problem was the other room, actually. I haven't heard any complaints so far. I think has been okay.
Yeah, that was much better, Francisco.
Yeah, okay. So that it was a learning experience. So I have to prepare my whiteboard in this room, which I can do for next time. So
sounds like a plan.
Okay, so now just reflect a little bit of what we have heard about the simplicity to complexity in the development of the universe, the origin of the things that we can see, and how small things can be. I mean, I can tell you very quickly now, we can repeat this again next time, but we said this enormous amount of millimeters between here and the nearest star, which is equivalent to the number of molecules of water in a little droplet of water that is hanging from a spider web. That's small, but the water molecule is made out of atoms, and the atoms are smaller than the molecule, and the atoms are made out of protons and neutrons, electrons, and this nucleus of the atom, the proton and the nucleus of the atom is far smaller than the atom, so it breaks your brain, really, because impossible to imagine. I'm going to show you that image again, but I put this image in your brain. So take the atom of carbon, for example. You see 6 protons, 6 neutrons in the nucleus of the atom. This is very much out of scale. And the electrons around, and the cloud that we see here, this fuzzy thing that we see here, kind of atmosphere, is the atom itself. This is the size of the atom of carbon with all these particles inside. If we put this to scale, try to follow me. I wish I had the pictures for this. I'll show the pictures next time. If the nucleus of the atom, any atom really of any chemical element really, could be uranium, could be hydrogen, doesn't matter. They're all, for the sake of this explanation, they are all the same. If the nucleus of the atom was the size of a grain of rice, okay, 2 or 3 or 4 millimeters in size, you picture that. Nucleus of the atoms with all the protons and neutrons, grain of rice. And you go and put the grain of rice in the center of Wembley Stadium. Okay, Wembley Stadium, big. I mean, it's probably 300 meters across, including the whole structure there. Grain of rice in the center of Wembley Stadium. Wembley Stadium, the size of the Wembley Stadium itself, including not only the field, but all the public places as well. So the nucleus will be the grain of rice, and the Wembley Stadium will be the atom. You picture that?
It's bizarre.
So, which means, essentially, that the atom is empty. It comes to that. There is nothing between the nucleus of the atom and the electrons. It's all empty space. And that is something that I'm aware of the time, actually, that is already 8 o'clock. I don't know if we need to stop at some point. I never covered what I wanted to do, but anyway, it gives you an idea of the scales in the universe, how small things can be. If you imagine that this will be the size of a Wembley Stadium, and this is the car park around, okay, the car park of Wembley Stadium around here, and inside the Wembley Stadium, at this scale, you imagine a grain of rice at the scale of the Wembley Stadium in the center here, and that is the atom, which means that you can get rid of the space, the empty space between the atoms, between the nuclei, between the atoms, and then put the nuclei of the atoms together, and that can be done. We have an example of that. And this is just to give you an idea of how bizarre the universe is, and how we have to really break our minds, and we have to cope with these impossible scales that we have, both in space and in time. And in their own right, in their own time, the protons and the neutrons are also empty. You see? The quarks inside the protons and the neutrons are minute compared with the size of the protons. So it's another scale to go even smaller and smaller. So that is the amazing story of the universe. There is another analogy. I mean, just to finish that, since we are breaking our brains already, let's break them even more. What's the population of the Earth at the moment? More or less 7,500 million people, yeah?
Yeah.
Take all the atoms of all the people alive today, all the carbon and hydrogen and oxygen and nitrogen, calcium, phosphorus, mainly, of all the people alive today. 7,500 million people. How many atoms is that? Imagine that. We were talking about millimeters from here to the that was only molecules. Once you have all the atoms of all these people together, get rid of the empty spaces, get rid of the electrons, and bring the nuclei of all these atoms together. So you get a mass of protons and neutrons with no empty space in between. Okay, just try to imagine that you do that. You get all the protons, neutrons of all the atoms of all the people alive today. I'm trying to get a little prop here. You get a mass of protons and neutrons. What is the volume that those protons and neutrons of all the atoms of all the people, what is the volume that all those protons and neutrons will occupy?
One golf ball.
One what?
A golf ball.
Wow.
Oh.
So in this little ball, which is barely a centimeter, we could fit all the protons and neutrons of all the atoms of the entire humanity.
Would that be enough to start a black hole?
You wouldn't be able to lift it.
And you know what? That material exists. It exists in nature. Imagine the weight of this little volume with all the weight of all the people, the density of this little ball. What we call that is a neutron star. And we will see that neutron star when we go into the course later. But just to give you an idea how empty it is. And those protons and neutrons are empty themselves. So then we go to the next stage, which is the black hole, and these bizarre things that we just discovered a few decades ago. So that's amazing. So anyway, just give you a bit of a flavor of what the course is about. It's about the history of all this, how these atoms get together, how the stars produce the atoms, how the stars evolve and develop and explode and get born again, and all these processes that go on and on and on in the universe, how the stars and the planets are formed, how the planets develop environments, how the environments develop life, and how life develops people like you and I that are able to think and to imagine and to come to these conclusions, which are based in very strong pieces of evidence. I find it fascinating. So I will leave you there. Let's have a little bit of a reflection on what we said. See if you have anything to say. You can open your cameras now. I think the problem of bandwidth is gone. I think it was my fault by having the wrong room. So see, we open all the cameras. We shouldn't have any problem now. See, we can. If this is a good test for what we are.
Oh, you've been very clear since you moved. It really has been good.
I think yeah, that was a learning experience because I have been doing it all the time, but never in that room. That's the problem. Okay, thank you very much for that. Yeah.